Hey everyone, this is Dr. Walker. In this video, we're going to do an example of finding the electric field due to a continuous charge distribution, and it's going to be a line charge. Let's take a look at the example. We're trying to find the electric field above the midpoint of a charge rod. We're trying to find the electric field at point P, which is a distance h above the midpoint of the straight line segment that has a length L and carries a uniform line charge density lambda. The first thing I've done is I've written down the equation that we've found to find the electric field due to a continuous charge distribution. But this is our first example of learning how to use this equation. The first thing I want to mention is that we can rewrite this if we realize that the electric field is the integral of dE. Then we can write dE as ke dq over r squared. And the reason this is useful is we can go ahead and use this expression, write dq in terms of the variable that we're going to be integrated over once we make all of those substitutions, and this expression looks the way we want to, then we'll go ahead and integrate. Just that way we don't have to rewrite the integral a whole bunch of times. Okay, so we want to find a dE due to a very small charge element dq. So the first thing to do is to look at our charge distribution and consider several little charge elements on this charge distribution, because we know that it's divided into a whole bunch of them. In this example, I'm just going to assume a positive charge. So if we have a dq over here, we know that it produces an electric field in the r hat direction, and it points away from the charge element. So this would be dE1 if this is dQ1. And then if we have another charge element here that we call dQ2, then it would produce an electric field dE2 pointing in the opposite direction. The reason that it's useful to draw a couple of dEs is that we can discover if there is any symmetry in the problem that will help us simplify the problem. In this case, what we notice is that every little charge element on the left-hand side produces a field that points to the right, while every charge element on the right-hand side produces a field pointing to the left. All of those x components, assuming that the x is horizontal and the y is vertical, all of the x components are going to cancel out, and we're only going to be left with a y component for the electric field. So that's the first thing to do, is to see, is there going to be any symmetry in the problem? And we can find this out by just drawing a few charge elements and looking at which way all of the dEs are going. So since we have found some symmetry, what we can do is we can just consider the electric field due to 1/2 of the segment. We can completely disregard 1/2 of it. And then once we find the electric field due to this 1/2 in the y direction, then we can multiply it by 2 because we know that the right-hand side contributes the same amount. So let's go ahead and do that. We're going to erase all of the ones on the left side and just figure out how to solve for dE. We can just call it dE now instead of dE1. So we're going to go over here and we're going to write dE is equal to ke dq over r squared. At this point, we can go ahead and rewrite dq as lambda dl, which is what we learned for charge that distributed along a line, but instead of calling this charge element having a size dl, we can say that it has a size dx because we're going to be integrating along the x direction. So we're going to write lambda dx for dq. This is going to be over r squared. So now the next thing is we said that we're only going to look at the y components because all of the x components are going to cancel out. So let's go ahead and write an expression for the y component. What we need to do is we need to introduce an angle. So let's go ahead and consider the distance here between the DQ and the point P. Let's call that distance R. And let's define an angle theta up here. And then we see that this is the same theta over here, and that DEY is going to be adjacent to the angle, and it's going to be DE cosine of theta. So we can write KE lambda dx over r squared times cosine of theta. So this is going to be DEY. Eventually, we're going to have to multiply by 2 to find a contribution of both segments. Before we're ready to integrate, we need to write all of the variables that depend on x. We need to write them in terms of x. We know that we're going to be integrating from 0, we can call this 0, to L over 2. So any variable that depends on x, we need to rewrite it in terms of x. We know that KE and lambda do not depend on x, but cosine of theta and r squared do depend on x. So let's go to the side here, and let's rewrite cosine of theta. Let's actually write it a little bit over here so we have more room later. Cosine theta is adjacent over hypotenuse, so h over r. And our r depends on x, right? So r is the hypotenuse, and then x is over here. So r is the square root of x squared plus h squared. So we can also write cosine of theta as h over square root of x squared plus h squared. Now we can go ahead and rewrite our expression here. We're going to put cosine of theta as h over square root of x squared plus h squared. And then our r squared is going to be this squared. That's going to get rid of the square root, so it's going to be x squared plus h squared. And then we have our dx. So now we can simplify one more time and combine those two expressions in the denominator. And we're going to get x squared plus h squared to the 3/2. So now we have rewritten this expression so that we have constants and the variable h, the variable x that depends, that we're going to integrate over. Now we're ready to write the integral. So the integral E is going to, the field E is going to be the integral of dEy. So anything that doesn't go into integral, we can already take it out. Any constant, ke lambda h. Then we're going to integrate dx over x squared plus h squared to the 3/2. And let's not forget, at this point, we could have done it earlier, but we said that since we're integrating from 0 to L over 2, that we're going to have to multiply this whole integral by 2 to account for the contribution of both halves of the rod. Okay, so how do we integrate this? This is a more complicated integral that would require a substitution using secant squared function, but hopefully you have an integral table or a software that can perform this integral for you. And you will see, if you use this integral table, that this integral is equal to x over h squared times the square root of x squared plus h squared. we're going to integrate from 0 to L over 2. So this is a very common integral, so you should be able to find it in some integral tables. So let's finish this up over here. We can cross out the h here, and then let's see what we have. E is equal to 2 ke over h, and then the x is going to go L over 2 over, then we're going to have L squared over 4 plus h squared, and take the square root of all of this, minus 0. So this is going to be, the last thing we can cancel out is the factor of 2 over here. So we're going to get KEL over h, and then we have the square root of L squared over 4 plus h squared. Let's not forget that the lambda over here that I was looking for it, there's a lambda right there. And let's not forget a direction. We know that the electric field is going only in the y direction, so we can just say that it is in the k direction. So that is the answer for the first part of this question. The electric field due to the segment that has a finite length, and we're looking for the field at a distance h. There are two more parts to this problem. Let's take a look. In the next part, we're trying to find an expression for the field if the point P is very far away from the rod. So what I've done is I've written down our result from part A, and what happens if the point is very far away, over here somewhere. What that means is that h is going to be much greater than L, so we need to see what happens to this expression. So what we can do is we can rewrite these variables here, and then we can look in the square root here and notice that if h is much greater than L, then this L squared over 4 is going to be insignificant compared to h squared. So we're just going to have the square root of h squared in the denominator. This is going to be insignificant. So the square root of h squared is just h. So we're going to get ke lambda L over h squared. So what is significant about this is, first of all, if you see lambda times L, you know that this is equal to charge, Q. So the field, when you're very far away from this segment, it looks like KQ over R squared. It looks like the field from a point charge, which is what we would expect when we're very far away from that rod. And lastly, let's look at part C. This time we're deriving an expression if instead of having a rod, we have an infinite line of charge. So what I've done here is I've written our result again from part A, right when we were about to take the limits of the integration from 0 to L over 2. But this time, since we have an infinite line, we can just change the limits of integration and say that we're going to integrate instead from 0 to infinity, and then still have twice that contribution. And if you're wondering, what is the point of this being an infinite line of charge, this is an approximation that can be very useful when your point P here, when it's very close to the rod, then from the perspective of that point, it's as though this line is infinite. So sometimes very useful to approximate things as being infinite in size. Let's see what happens when we have changed the limits here of the integration. We get 2 ke lambda h, and then we get infinity over infinity squared plus h squared, so the h squared here becomes irrelevant. We have infinity over infinity. All of this is equal to 1. So the final answer for the field above the midpoint of an infinite line of charge is 2ke lambda over h. So what is interesting here is that now the field depends on the distance. It doesn't have a r squared dependence. It depends simply on that distance. That's it for this example. We have several more in the following videos for different charge distributions.